All right, let's get started on topic 4, which is called the ideal gas law, and it will be on page 12 of your notes. So, did you know that when a gas is contained and not undergoing any specific changes, there's a very specific relationship among pressure, volume, number of moles, and temperature? And this is represented mathematically with what's called the ideal gas law. So we are talking about if you have a gas in a container. So I like to picture like maybe a canister of CO2. I get these shipped to my house to make fizzy water. So if I have a canister of CO2 and it is just sitting on my kitchen counter. So here's my kitchen counter. It's just sitting there and it's doing absolutely nothing. I'm not heating it. I'm not releasing it. I'm not changing the temperature, I'm not changing the volume. It's literally just sitting there. It has 4 variables: pressure, volume, the number of moles, that's how much CO2 is in that canister, and the temperature. None of them are changing. When we are under these static conditions, there is a very clear mathematical relationship between these variables, and again, it's called the ideal gas law. So let's take a look at what that equation is. The equation for the ideal gas law is PV equals nRT, and we call this the ideal gas law. We sometimes call it PUVnert or PERVnert. It's got some funny names. So all of the variables are what they always have been. P stands for pressure. Now, pressure in this particular scenario must be measured in ATM atmospheres. If you are given pressure in a different unit, you must convert it to atmospheres to use it in the ideal gas law. Next up is V for volume. It must be measured in liters. So if you're given volume in maybe milliliters or cubic centimeters, you must convert it to liters before you use the ideal gas law. Next up, we have N. N stands for the number of moles of the gas. It must be moles. If you're given something different like grams, you must convert it to moles before you can use it. And then I'm going to skip R for a moment and let's talk about T. T is temperature, of course, and it must be in Kelvin. If you have temperature in a different unit, you must convert it to Kelvin before you can continue with the ideal gas law. All right, so let's talk about that last variable. I'm going to erase all my color coding so far, and let's talk about the R value. R is a constant. It is always the same number for the ideal gas law. It's, as you can see over here in the diamond, it's called the gas constant. And again, it's a very specific number. It is 0.0821. That number is not going to change for us. It will always be 0.0821. It is the mathematical relationship between these 4 variables. So you don't have to think about it too much. The only disclaimer I will say is it only works if your pressure is in atmospheres, your volume is in liters, your moles are in moles, and your temperature is in Kelvin. If you did not convert everything to those units that I've highlighted in orange, R is not going to work, and you're just not going to get the right answer. So you have to be careful to look out for those proper units. All right, this is kind of an example of the ideal gas law in action. I always like to know, how does this apply to real life? So in refrigerators or air conditioning units, there's something called a coolant, and that coolant gas is compressed. So we have to plug in air conditioners or refrigerators, and that energy from the plug is used to compress the gas. And that causes its temperature to increase. So if you've ever noticed, like on the back of a refrigerator or something, it kind of feels warm. This is why. That hot gas is then passed through a radiator, and the gas is allowed to expand. As the gas expands, it cools off, okay? So as temperature decreases, volume is increasing, and that heat that it uses to expand is from the interior of the refrigerator or the house, and therefore the temperature decreases. All right, we're gonna skip this activity if you are just watching the video to get caught up or whatnot. So let's just move on. And we are just going to jump right into solving some problems. So the key thing to remember is that we use the ideal gas law, PV equals nRT, if we have a word problem describing a gas that is undergoing no changes. It is just sitting there doing nothing. So let's see. Problem 1 here says a 4.4 liter container holds 15.4 grams of oxygen gas at a temperature of 22.55 degrees Celsius. We're going to have to fix that. Calculate the pressure. All right, so this is just a container holding a gas. There's no changes, so I'm definitely going to be using the ideal gas law. All right, to do the ideal gas law, you need to make a list of your variables, P, V, N, R, and T, and we need to get everything into the proper unit. So pressure is supposed to be in atmospheres, but that's actually our unknown because it says calculate the pressure. So I'm just going to put question mark ATM. V is our volume. That's going to be 4.44 liters. That's the proper unit, so I don't need to make any changes there. N is number of moles. Well, here we go, y'all. I do not know the number of moles. Instead, what I'm highlighting in red here is a number of grams of oxygen, but I need to convert that to moles. And so let's go ahead and do that. I'm going to do that in this little cloud down here. I have 15.4 grams of oxygen. All right. So if I have 15.4 grams of O2, how do I convert that to moles? I do a dimensional analysis molar conversion. So I bring down grams of O2 and I go to moles of O2. The numbers that we use to do these conversions, 1 goes in front of moles, and in front of grams is the molar mass of the chemical. Oxygen is O2, that's 32.00. All right, so I'm going to take 15.4 divided by 32. So 15.4 divided by 32, my number of moles is 0.481. 0.481. And that's moles. Okay, so 0.481 is my number of moles. Sometimes they'll give you moles, other times, like now, they give you grams and you have to convert. All right, moving on in our list. R is always the same. It is 0.0821. The unit for it is liter atmosphere over mole Kelvin. That's just our reminder that those are the units we have to use. All right, finally, we have our temperature. This temperature is so cringeworthy. The temperature is 22.55 degrees Celsius. No way. I am going to add 273 to get my temperature in Kelvin. So 22.55 plus 273 gives me 295.55. 295.5 Kelvin. All right, y'all, we are ready to solve this problem. The next step would be to take our list and substitute it into PV equals nRT. So here we go. P is still our unknown, so I'm going to leave it as is. I like to put these numbers in parentheses as I solve them just to kind of keep them separate. Volume is 4.44 liters equals, my number of moles is 0.481. My R value is 0.0821, and my temperature was 295.55. All right, so I have pressure here, and I need to get it by itself to solve. So it's multiplied by 4.44, so I need to divide both sides by 4.44. So divide both sides by 4.44. So that one cancels. Excellent. All that's left here is pressure. So I have that pressure equals 0.481 multiplied by 0.0821 multiplied by 295.55 and divided by 4.44. Go ahead and grab your calculator, pause this video, and solve in your calculator and see what you got. All right, so our pressure is 2.63, and the pressure in an ideal gas law scenario is in atmospheres. So 2.63 atmospheres is our answer. Nice job. Let's move on and try number 2. Number 2 says a tank of hydrogen, H2, has a volume of 22.99 liters. I'm going to go ahead and label volume, and holds 14 moles of that gas. 14 moles, that's going to be our N value. The pressure in the tank is 14.3 atmospheres. I'm going to label that P. What is the temperature in both Kelvin and degrees Celsius? So we're going to solve for the temperature, and we need to make sure that we report it in both ways, Kelvin and Celsius. All right, how do I know that I need to use PV equals nRT? I want you to think about that for a second. Why do I use this equation? I'm using this equation because there are no changes going on. Read that problem. Nothing's changing. It's just a gas. It's just sitting there. It's doing nothing. So we're going to use the ideal gas law. So let's make our list. P, V, N, R, T. Let's go ahead and fill in R. We already know it. It's 0.0821 liter atmospheres over mole Kelvin. I like to call that latums over molks. And let's plug in what we know. So starting at the top of the list, do we know our pressure? We do. It's 14.3 atmospheres. Okay. Next up, V. Do we know our volume? Yes, we do. It's 22.9 liters. Next up, N stands for number of moles. Do we know it? Yes, we do. It's 14.0 moles. All right, and finally, temperature. We don't know our temperature. I'm going to give it a question mark. And what unit is that temperature going to be in when we solve it? Well, because it's the ideal gas law, it's going to be in Kelvin when we solve it. All right, so let's substitute into PV equals nRT. P is 14.3 atmospheres. V is 22.9 liters equals N is 14.0 moles. R is 0.0821. And temperature is our unknown. Okay. Temperature is multiplied by 14 and 0.0821. That's all multiplied together. So how do we get T by itself? We have to divide by these two numbers. So I'm going to divide both sides of the equation by 14 and 0.0821. I'm going to do that on both sides. 14 and 0.0821. Cross, 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 cross. All right. So I get 14.3 times 22.9 divided by 14.0 and divided by 0.0821. All right, again, pause the video, calculate, see what you get. We've got 14.3 times 22.9 divided by 14 and also divided by 0.0821. We get 285. Now, that is our temperature in Kelvin because the ideal gas law solves for Kelvin. We also want to give our answer in Celsius. Okay, this is our answer. We need it both ways. So to solve for degrees Celsius, that's going to be 273 minus, it's Kelvin equals degrees Celsius plus 273. So Celsius is Kelvin minus 273. So I'm going to subtract 273 here. 285 minus 273 gives me 12. So 12 degrees Celsius. All right, so that is my answer. And we are ready to do our last problem. All right, last one says find the volume of 85 grams of oxygen at 25 degrees Celsius, and 104.5 kPa. All right, this is just a gas sitting there. Nothing is happening. So it's the ideal gas law, PV equals nRT. 85 grams of oxygen is mass, but I'm going to be able to convert that to moles. Okay. Celsius, let's just go ahead and solve that. Let's add 273 to convert it to Kelvin. That's 298 Kelvin. That's my temperature. And 104.5 kPa, what is that measuring? That is the pressure. But notice that it's not in the right unit. We're going to have to work on that. All right, so let's make our list. P, V, N, R, T. Okay. Pressure is not in the right unit. 104.5 kPa. I'm going to solve that to atmospheres down here. 104.5. 104.5 kPa. We're going to convert to atmospheres for the ideal gas law. So 1 atmosphere equals 101.3. That's the conversion factor. So 104.5 divided by 101.3, do that in your calculator with me, pause, is 1.032. 1.032 atmospheres. Okay, the other conversion that I'm going to need to do, let's go ahead and do it, is the mass to moles. I'm going to do that down here. 85 grams of oxygen. Let's convert that. 85 grams of oxygen. I need to convert it to moles. So mole to gram conversions, I use 1 mole and the molar mass. Just like before, molar mass of oxygen is 32. So I'm going to divide 85 divided by 32 to get my number of moles. It's 4.0 moles of oxygen. All right, so those are 2 little numbers that I converted down there in the clouds. I'm just going to use those in my list. All right, so the pressure in atmospheres was 1.032. The volume, I don't know it because it says find the volume, so question mark liters. Number of moles, I solved for it, it was 4.0 moles. R is 0.0821 liter atmospheres over mole Kelvin. And temperature is 298 Kelvin. All right. Next step is to substitute into the ideal gas law. So that's pressure, 1.032 atmospheres, times volume, just V, equals number of moles, 4.0, times R, 0.0821, times temperature, 298. Okay, we're so close, y'all. How are we going to get V by itself here? Well, we're going to use our algebra. V is multiplied by 1.032. We need to divide by 1.032. Divide both sides by 1.032. Cancel, cancel. All right, so what's left over? V equals 4.0 times 0.0821 times 298 divided by 1.032. All right, pause, grab your calculator, let's solve it out. All right, our volume is 94.8 liters. Nope, what did I mess up? 85 divided by 30. I messed up my moles, y'all. Okay, follow along with me real quick. My moles is 85 divided by 32. That's 2.65. Moles, 2.65. Moles, 2.65. Moles, 2.65. Okay, let's recalculate. This is a good example of everybody makes mistakes sometimes. Just fix it when you need to. So we've got 2.65 times 0.0821 times 298 and divided by 1.032. We get 62.8. Volume, 62.8 liters. All right, y'all, thanks for watching. Hope this was helpful in learning the ideal gas law. If you have any questions, let us know. Thanks for watching. See you next time.